Welcome to today's paper reading. Today's paper is titled, Retrieval-Augmented Generation for AI-Generated Content, a Survey. This paper, titled Retrieval-Augmented Generation for AI-Generated Content, a Survey, was published on the AR14 preprint by Penghao, Zhao and colleagues from Peking University and Tencent Inc. The paper addresses the challenges faced by artificial intelligence-generated content, AIGC, such as updating knowledge, handling long-tail data, and mitigating data leakage. It introduces the Retrieval-Augmented Generation (RAGE) paradigm, which enhances the generation process by retrieving relevant objects from data stores, thereby improving accuracy and robustness. The paper provides a comprehensive review of existing RAG techniques, classifies RAG foundations, and summarizes enhancement methods, offering valuable insights for both researchers and practitioners. The recent surge in interest around artificial intelligence-generated content, AIGC, has led to the development of various content generation tools across multiple modalities. These include large language models like GPT and Llama for text and code, and models like DALL-E and Stable Diffusion for images. However, AIGC faces challenges such as outdated knowledge and risks of data leakage. Retrieval-Augmented Generation (RAG) aims to address these issues by providing a flexible data repository that acts as non-parametric memory, easily updatable and capable of encoding confidential data. RAG also reduces the size of large models and supports long contexts, making it a promising solution for enhancing AIGC. Figure 1 illustrates the generic Retrieval-Augmented Generation (RAG) architecture. User queries, which can span various modalities, are input into both the retriever and the generator. The retriever's role is to extract relevant information from data sources. This retrieved information then interacts with the generator, which ultimately produces outcomes across different modalities. This process highlights how RAG enhances the generation process by incorporating relevant data, leading to more accurate and robust outputs. The RAG system is composed of two main components, the retriever and the generator. The retriever's role is to search for relevant information from a data store, while the generator is responsible for producing the required content. In the context of RAG, various generative models are utilized, such as transformer models for text-to-text tasks, LSTM for handling long-term dependencies, and diffusion models for creating diverse data samples. On the retrieval side, methods include sparse retrieval using metrics like TF-IDF and BM25, dense retrieval employing dense embeddings and ANN indices, and other techniques such as edit distance and named entity recognition. Figure 2 illustrates the general architectures of several generators used in the RAG system. Transformer models, known for their self-attention mechanisms, produce output sequences through vocabulary classification. LSTM models, a type of RNN, manage long-term dependencies with gating mechanisms and cell states. Diffusion models gradually reverse the noise addition process to generate new data from noise, based on probabilistic modeling and neural networks. The methodologies of Retrieval-Augmented Generation (RAG) are categorized into four foundational classes: query-based, latent, logit, and speculative RAG. Each class integrates retrieval information differently, such as through query augmentation or logit manipulation during decoding. These methodologies are applied across various modalities including text, code, image, and 3D generation, enhancing the integration of retrieved information with generative models. Enhancements to RAG systems are grouped into 5 areas: input, retriever, generator, result, and the entire pipeline. Techniques like query transformation and recursive retrieval aim to improve the quality of retrieved content, while hybrid and adaptive retrieval methods optimize the use of multiple retrieval strategies. Applications of RAG span diverse fields, leveraging iterative and adaptive processes to enhance tasks such as question answering and content generation. Figure 3 presents a taxonomy of RAG foundations, categorizing them into 4 main classes: query-based RAG, latent RAG, logit-based RAG, and speculative RAG. Each class is designed to integrate retrieved information into generative models in different ways, enhancing the model's comprehension and the quality of generated content. The taxonomy also highlights the application of these RAG foundations across various modalities, including text, code, image, and audio, demonstrating their versatility and effectiveness in different fields. Figure 4 presents a taxonomy of enhancements for Retrieval-Augmented Generation (RAG) systems. The taxonomy categorizes enhancements into 5 groups: input, retriever, generator, result, and the entire pipeline. Key points include input enhancement through query transformation and data augmentation, retriever enhancement via recursive retrieval and chunk optimization, and generator enhancement with prompt engineering and decoding tuning. These enhancements aim to improve the performance and efficiency of RAG systems across various modalities and tasks. The applications of Retrieval-Augmented Generation (RAG) span various modalities, focusing on enhancing tasks across text, code, and knowledge domains. In text applications, RAG is utilized for tasks such as question answering, fact verification, and common sense reasoning. For code, RAG improves tasks like code generation, summarization, and completion. In the realm of knowledge, RAG aids in knowledge-based question answering, open-domain question answering, and table-based question answering. These applications demonstrate the versatility and effectiveness of RAG in augmenting various natural language processing and computational tasks. Figure 5 illustrates the architecture of the retro model, which is designed to enhance question answering tasks by integrating the question with relevant retrieved documents. The model uses attention mechanisms to combine the query with the retrieved content, employing a chunked cross-attention (CCA) mechanism to facilitate this integration. Additionally, Retro incorporates a frozen Qinhan retriever to fetch the most relevant text chunks from the dataset, ensuring that the retrieved information is both pertinent and comprehensive. This architecture allows Retro to produce more accurate and contextually appropriate answers by leveraging both the query and the retrieved documents effectively. Figure 6 presents the architecture of the Re2Com 101 model, which is designed for code summarization tasks. The model retrieves similar codes using the BM25 algorithm and generates summaries using a long short-term memory (LSTM) network. This approach involves separately encoding the input code, retrieved code, and corresponding summary, then combining the hidden states or logits in the decoder to produce the final summary. Figure 7 illustrates the architecture of the KG5D model, which is designed for knowledge-augmented open-domain question answering. The model integrates retrieved triplets from a knowledge graph into the input for the decoder. It employs the fusion encoder technique, which combines the retrieved information with the input question to generate the final answer. The process involves iterative retrieval and re-ranking of the data to ensure the most relevant information is used for answering the question. Figure 8 illustrates the architecture of the Extra 308 model. This model employs a clip vision encoder and a LLM decoder, utilizing retrieved captions as input-specific in-context examples. The architecture is designed to enhance the model's ability to process and generate captions based on visual inputs. Figure 9 illustrates the architecture of the Animated Story 174 model, which is designed for text-to-video generation. The model simplifies this process by dividing it into two main components: plot-based video augmentation and video diffusion generation. The former enhances the video content based on the plot, while the latter generates the video condition on both the text and the video inputs. This approach allows for more controlled and contextually relevant video creation from textual descriptions. Figure 10 illustrates the architecture of the Reaudio LDM model, which is designed for audio generation tasks. The model employs a dense retriever called CLAP to fetch relevant caption audio pairs for the generation process. Additionally, the Make an Audio component retrieves audio samples based on text prompts and constructs pseudo-prompts to train a text-to-audio diffusion model. The architecture also includes a V8 decoder and Hi-Fi GN, which work together to synthesize high-quality audio outputs. Figure 11 illustrates the architecture of the AMD 115 model, which integrates two motion diffusion models. One model operates directly on the original prompt, while the other breaks down the prompt into anatomical scripts and retrieves similar motions. This dual approach leverages semantic modulated attention and condition mixture guidance to enhance motion generation. The architecture's design ensures that the model can effectively synthesize motions based on complex prompts, contributing to advancements in 3D asset generation. Figure 12 illustrates the architecture of the RetMol model, which integrates a lightweight retrieval mechanism and molecular strings into a pre-trained encoder-decoder generative model. This model retrieves and fuses exemplar molecules with the input molecular strings, enhancing the generation process for molecular design tasks. In this section, we discuss various benchmarks for RAG. Qinhan et al. Proposed a benchmark evaluating RAG across 4 dimensions: noise robustness, negative rejection, information integration, and counterfactual robustness. RetMol integrates a lightweight retrieval mechanism with molecular strings into a pre-trained encoder-decoder model. Additionally, RAGAs, ARIES, and TrueLens evaluate RAG on aspects like faithfulness, answer relevance, and context relevance using a separate evaluator LLM. The Retrieval-Augmented Generation (RAGE) system, despite its widespread adoption, faces several inherent limitations. Firstly, noises in retrieval results can introduce irrelevant or misleading information, which can affect the system's performance. Secondly, the retrieval process adds extra overhead, increasing latency and complexity, especially when combined with enhancement methods. Additionally, the gap between retrievers and generators requires meticulous design and optimization. The system's complexity is further increased by the need to tune numerous hyperparameters. Moreover, the lengthy context in RAG can slow down the generation process and is not feasible for generators with limited context length. Looking ahead, future research should focus on novel augmentation methodologies, flexible RAG pipelines, and broader applications to address these challenges and fully exploit RAG's potential. In this conclusion, the authors have conducted a comprehensive survey on Retrieval-Augmented Generation (RAG) within the context of Artificial Intelligence-Generated Content (AIGC). They have systematically organized and summarized the foundational paradigms in RAG, providing valuable insights into the interaction between retrievers and generators. Additionally, they have reviewed various enhancements that significantly improve the effectiveness of RAG, whether through component-specific improvements or pipeline-wide enhancements. To support researchers across different domains, the authors have showcased practical applications of RAG across a variety of modalities and tasks. They have also presented existing benchmarks for RAG, discussed current limitations, and highlighted promising future directions for further research. Thank you for watching.